All right, cool, we'll get started. So, Beefy ML. Just before we get into the presentation, I guess I've got a couple of quick disclaimers. So, you may have noticed that the name on the title slide, the company does not match the name on the presentation, on the schedule. So, all of this work I'm presenting here was done under the auspices of the CSIRO, which is Australia's national research organisation. I'm no longer an employee. I'm presenting this in a personal capacity. And all this work was funded by the CSIRO. And just for some of the numbers may jump around a bit for algorithms and stuff. There are multiple algorithms over time, and that's why they may not match up a bit. Especially in the ag tech space and machine learning and engineering, this is never a one-man show. There's always multiple people involved, lots of expertise. I'd just like to acknowledge Greg Bishop-Hurley, who's been the project leader for this, our main agriculture contact, and Reza Arabuli, who's our main, who was our main machine learning and research scientist. So, machine learning on cattle, why do we care? So, as I'm sure all of you are aware, cattle are a very emissions-intensive source of protein, but there's things that farmers can be doing to sort of improve that situation. Selective breeding is definitely one of those things, which is best, and the way that can be improved is sort of feed efficiency. So how much grass does it take for a cattle to eat for it to put on 1 kilo of mass? If you can improve that ratio, then the emissions per kilo go down. Some of these things are relatively easy to measure. Weight gain, for example. Walkover weighers are relatively common equipment on farms. As many of you may know, that's not a cow, that's a sheep, but it's the general idea. They walk on a bridge, it weighs them. But the amount of food that the cattle eat, it's something that's much harder to quantify. Even if farmers wanted to stand around in the sun all day, they don't have the time or even necessarily the expertise to sort of measure how much is going into each cow. And obviously, each farm has hundreds, thousands, tens of thousands in some cases, cattle. So it's not a scalable solution. So if we're trying to calculate this sort of feed efficiency metric, how do we actually get out the amount of food which is going into the cattle? And in an ideal world, you can basically calculate this by how long was the cow grazing for, how often is that cow biting, and how much is that cow biting per bite. But what do we actually have to measure that with? And in reality, all you really have is an IMU. For a lot of this stuff and then from the IMU, you sort of try and calculate how long the cow was grazing for, how much it's biting, and then you sort of apply some scaling factors of how efficient is this pasture, essentially. Right now, we're basically just using IMU data. In an ideal world, you would have a measure of what sort of pasture is this cow grazing in, how good is that pasture, i.e. if it's rained over the last month, you're gonna have nice, thick, lush grass. If you're in the middle of a drought, it's gonna be quite sparse. And that's really gonna affect how much dry matter is actually going in. But this talk is really about the machine learning magic in the middle there. So given IMU data and some magic, how can we get out to time spent grazing and a bite rate? So obviously to have machine learning on cows, you need some hardware. And this project utilizes two main categories of hardware. So one of those is a research collar. So this is a big collar that goes on the cow's neck. I've got some photos a little bit later on. It's had many iterations over the years, all of them except for the Loki 2 of running Zephyr. So that's been a really great transition for us. But even the collar with its relatively large size is still quite resource constrained, right? You've got 1 megabyte of flash, 256K of RAM. And these things have to sort of be able to survive for multiple months out in the paddock without really any human interaction. So they are indefinitely powered off solar. They've got a relatively beefy lithium-ion battery in there. And low power IMU contact logging, and they log all this data to the SD card. And the other useful information there is, I guess, is the sort of 1 Hertz GPS trace. So over the course of months, you can track where these cows are going over time. The second piece of hardware, I guess the other thing we should note about this is that this is a relatively expensive piece of kit. It's a big collar, you got weights, you got webbing for the thing which goes around the neck. So it's not a scalable solution, and they have a tendency to fall off over time. The fabric gets ripped, so it's not a scalable solution. It's a great research platform. But for selective breeding and stuff to take place, it needs to be a scalable solution, right? So that's where the second product comes in. So the Ceres tag is a commercial product. I've got one in my hand. Again, it's a resource-constrained platform, 1 megabyte flash, 256K RAM. As it's a commercial thing, it goes on the ear of cattle. Again, needs to run indefinitely off solar power. So it's got a rechargeable LiFi battery in there, low power accelerometer, super light, less than 30 grams. It was originally designed for cattle, but as you hopefully can see in the ear of that giraffe, it's not the only place it's been deployed. I guess the other cool thing about this platform is that up on the top right there, you can see it's actually a direct-to-satellite platform. So it doesn't matter where in the world these tags go. There's no infrastructure required. It can report its location up to 6 times a day, direct through satellites, which is pretty cool. And until it was made, not many people thought it could happen. So obviously, to have a machine learning algorithm, you need data to train that algorithm on and to validate what you're generating. So this has been a project inside of CSIRO for a long time, over more than a decade. I think up to now, there's been sort of over 100 sort of multi-month deployments of these collars all across Australia. There's even one currently going on in Switzerland. And each of these deployments is sort of consisted of, you've got the raw data being saved to these collars, but you also need annotated data in order to train these models. And depending on the experiment, this can be anything from 24/7 video recording with later annotation. It can be farm workers wandering around with a notebook and going, this cow is eating now, this cow is drinking now, etc. And then you've also got the automated data, so the walkover ways are a good example of that. But the data collection is actually a big problem for the ear tag solution, right? These things are ultrasonically welded shut. They're completely sealed. You can't get out of them. And they've only really got enough data on there for maybe a few hours, enough space on there for maybe a few hours worth of data. So what we actually do is we have when we're generating data, we have an ear tag together with a collar. Those two things pair over Bluetooth. And the ear tags actually stream their raw accelerometer data over Bluetooth to the collar and save that data directly onto the collar's SD card. So at the end of the trial, you pull the collar off, decode the SD card, and then you've got your 2 different data streams, one for your collar samples and one for your ear tag samples. So just to give you a bit of an idea of what a trial like this looks like. So on the left there, we've got an example of a bunch of collars. So that sits on the neck. You've got the webbing which goes around the neck of the cow. And then down the bottom, you've got a big weight to sort of try and make sure that that thing stays on top of the neck. Cows come through this is not a walkover way, this is a crush in this case. But basically it compresses their sides so they can't move too much. You install the hardware, off they go. So after you've installed it, you've got a bunch of cows. It's probably worthwhile noting that even though these things have literally just been deployed, there's quite a lot of variation in like how those collars are actually sitting on the animals. And you can also see ear tags in the ears of a lot of those. And then once they've been put through the crush, they're put back out to the pasture or whatever. In this particular experiment, they're being fed out of bins, and these things automatically track which cows are eating from which bin and how much they're eating at a time. So it's a way of ground truthing the algorithm. And then obviously, once they've been put out, you don't want to sit there and watch for 3 months while the cows eat. So we have some remote monitoring dashboards for where are the cows currently, what are the battery voltages doing, how much data is being logged, etc. So you can sort of go, okay, well, maybe this one or two collars is having problems, need to go out and fix that. If everything's all good, just let it run. I guess, so currently this data is all sort of reported through LTE. In the past, it's been through LoRaWAN. We just sort of use whatever makes sense at the time. So data processing. So we've got our data. What does our sort of processing pipeline look like? So we've got all our data on the SD card. We've got a bunch of annotations from a whole range of sources. We decode that binary format into a whole bunch of CSV files, too many to be honest, probably. And then we've got to sort of all rationalize all that data into a common format, which like Python training tools can use, for example. So there's a whole stage of pre-processing there. Then there's the actual iteration over the machine learning architecture. It's a lot of heuristic stuff. I think the next slide goes into a bit more detail. And you sort of validate the architectures you validate the architectures you're looking at against the data sets you have. After you've done that a bunch of times and you've sort of hit your either local maximum or hopefully global maximum of performance, you output the model structure and the model parameters ready to be put onto an actual embedded device. And you need different models because they're different devices. They're attached to the animal in different ways. So if you tried to run a collar algorithm on an ear tag, it's not going to go so well. So there's a whole range of algorithm like tweaking points of like ways of how you want to design this. We are focused on ultra low power devices, so the main constraint is how long does this thing take to run, and will it fit inside our memory? Obviously, a large language model is not going to fit on these devices, so it's an important process. Yeah, lots of features to tweak. It's not my area. I'm not into the details of it, but it's basically a combinatorial optimization problem. So you are trading off all these various issues to try and get the most performance you can out of this thing. Once you've got your algorithm, you need to obviously validate how well that matches the data you've generated. So to do that, there's a thing called n-fold testing. So you've essentially got your complete labeled data, and then you subdivide that. So this will be four-fold testing. So you subdivide that into different slots. You train your architecture on, say, 3/4 of the data, and then you evaluate it on the last quarter. You combine all those folds together, and you see how well that would have performed overall. And yeah, that's the iteration of the architecture of the algorithms. Now, there's lots of challenges with trying to design these sorts of low-power algorithms. Cattle are not necessarily cooperative test subjects. As I mentioned, the collars move around on the neck, ear tags move around the ear. In extreme cases, cows can bite through the collars of other cows. It's just a mess. Unbalanced data sets is also a real issue. Cattle don't spend the same amount of time grazing as they do drinking, as they do walking. They spend many hours a day grazing, but maybe 5 minutes drinking. So it's an important thing to recognize when you're designing these things. You could say it's 95% accurate, but it gets all of the drinking completely wrong. So you've got to be aware of that when you're evaluating the performance. MEMS accelerometers are also not ideal devices by any means. They have a whole bunch of variations with temperature. They've got nonlinearities, cross-axis sensitivity. Basically, what our machine learning guys said is basically individual samples are worthless. What you have to do is look at statistical properties over a window. If you're looking at individual samples, all you get is noise. And gyroscopes are apparently even worse. To date, we don't use gyros. We collect gyroscopic data, but the energy cost is not worth the, if any, performance gains. So how does this thing actually run on a device? So at a high level in our Zephyr application, we've got a task scheduling and configuration thing. So that controls sort of the parameters that the accelerometer is set up with, for example. So run at 50 hertz with a plus minus 4G range or whatever. That's reconfigurable on the fly. Also controls GPS and environmental sampling and everything else. So this scheduling basically triggers the IMU thread to run. That runs the IMU, generates data in big chunks, and shoves that off to our own data broker, which is basically ZBus, but written a few years before ZBus was out. At that point, we have a range of algorithm implementations which consume that data. They run the algorithm over the data and put outputs. And out of both the IMU thread and the algorithms, the outputs of these things are logged to both SD card, pushed out over Bluetooth, and reported back up over LTE in this case. The actual thread itself is relatively simple. It sits there waiting on, probably quite recognizable if you've used ZBus. You sort of sit there in the thread, you wait for new data, iterate over the samples, buffer it. Once you have enough data, you run the algorithm, log the outputs, clear the buffers, repeat as needed. The actual implementation of this is all just done, well, 90% of it is just CMSIS DSP. It's available straight in the Zephyr tree, super handy. And basically, the operations from, say, PyTorch map pretty directly to the CMSIS DSP functionality. If you have some form of hardware acceleration, you even get free hardware acceleration with the DSP stuff. So, so even stuff like convolution, matrix multiplication, hyperbolic tangents, it's all pretty easy to get going with. So for us, we sort of separated the whole process into two parts. There's the feature extraction and the classification. And then both of these C implementations are actually unit tested against outputs from PyTorch to validate that the performance you get in Python is actually the same as what you get on the end device. And that actually works really well. It makes it super easy to see whether your algorithm, your implementation is actually correct, because you can get it to basically identical outputs, even though one is Python running on your x86 and one is Cortex M4. We implement it on 32-bit floating point numbers. Our Nordic chipsets have a hardware floating point unit, so that makes that relatively efficient. We have in the past measured or attempted to implement, well, attempted. We have implemented it in quantized implementations, so 8-bit. You do get faster runtime. The weights are obviously much smaller, 8 bits versus 32 bits for the floating point. Your accuracy does go down very slightly, but not really enough to matter. But the main problem is that it's significantly more painful to implement. Because it's a quantized implementation, it saturates basically immediately. So especially if you're rapidly iterating on algorithm implementations, the cost of doing that is significant. So up until this point, 32-bit floating point numbers, and the performance numbers I'll give in a couple of slides' time sort of show that it doesn't really matter in the grand scheme of things. So depending on the model architecture you have, they can be very ROM heavy. For example, the example I had in the previous slide was 40 kilobytes for the model parameters. But that's basically driven by how large is your feature vector and how large do your matrices need to be. Obviously, matrix size is like a square thing, so if you can reduce that by a little bit, you get quite significant size savings. In terms of RAM as well, you can be you can reduce that quite a lot through intelligent reuse. For example, the architecture shown down the bottom there, you can sort of see that for each axis, once you've done the operation, you don't actually need that previous data anymore. So you can actually just ping pong your data back and forth between the buffers for each step. So you only actually really need one extra buffer here to hold all of your however many kilobytes of data. More complex architectures obviously need a bit more RAM because you can't just ping pong back and forth, but you don't need 12 buffers of 4 kilobytes or whatever. So how does the thing actually like perform in terms of efficiency? So the algorithms run over 5 seconds worth of data, but the whole process of the algorithm itself only takes about 20 milliseconds. So it's like that's a different it's quite different from what you might imagine from a large language model where you send off your result, a whole data center GPU cluster runs on it for a second or two, and you get back your response, right? It's much more efficient, and the weights and the DSP functions themselves are also like really efficient, right? Like this entire algorithm is sitting in more or less 3 kilobytes of ROM. And what that actually lets us do is have multiple algorithms compiled into the application at once, and then dynamically switch between them at runtime, depending on, like, for example, which breed of cattle the collar is on at that point in time. Yeah. So how does it actually perform, like, in terms of accuracy? Now, as I sort of mentioned earlier, it's a nuanced question to answer because you can say it's 95% accurate, but really it might just output grazing for every sample, right? So a better way of looking at that is this thing called a confusion matrix. On the left-hand side there, we've got what the animal is actually doing, and down the bottom, we've got what the algorithm is predicting. So it's quite easy to see here that the data sets are in balance. You can see that grazing and ruminating are far and away the most data points that we have. But in terms of like the errors as well, it's also interesting to look at what things are being mispredicted as. So for example, drinking, you can imagine a cow drinking, it looks much closer to an animal grazing than it does an animal walking, right? So trying to differentiate between these two behaviors is quite difficult. And you can see that in the, like how often drinking is misclassified as grazing, for example. Yeah, but at the end of it, you essentially get what was that cow doing for that window of time. You can push it over LTE, and then you get out a nice graph of what the animal is doing. I have no idea how long what timing is. 23 minutes, all right. I guess, any questions? Colors.
So you used CMSIS DSP directly. Why not use TensorFlow or one of those machine learning libraries that are available also for embedded systems?
Mostly because the machine learning part was done in Python. It wasn't done in TensorFlow. I expect if the training was done in TensorFlow, exporting that to TensorFlow Lite, for example, would be easier. But the models themselves are not that complex, as you can probably tell from the 20 milliseconds of execution time. So the cost of just writing the CMSIS DSP and unit testing it is relatively low in terms of effort. To get you get a new algorithm, new weights, new features, it might take an hour or two to do up the CMSIS DSP. It's not a huge overhead for the sort of stuff we're doing. If it was like image DSP, like feature, like digit extraction, I imagine that would be a nightmare to try and do in CMSIS DSP. But these things are small, they're compact and efficient. CMSIS DSP is what we've been using for that.
Right. One more question. Can I ask one? Sorry, yeah, one more question, just out of curiosity. I assume you have your own app repo with all of these libraries, the application itself, of course. Yep. And at first, did you systematically update the version of Zephyr you were using, or did you stick with one for the whole duration of this process?
Well, so as I sort of alluded to, this has been a sort of a decade-plus project. Right. The first research collar was running Kentucky, not Zephyr. Then it went to FreeRTOS and then finally to Zephyr. So as new releases come out, we have new application versions. It generally tracks the latest Zephyr release. Sometimes it falls behind by one version, but generally we want the new features, they're cool, they help us, so we keep updating.
All right, thanks.
Correct me if I am wrong, but you are also the maintainer of CMSIS NN in Zephyr, correct?
Yes, I am.
And you didn't mention that here at all, yeah?
No, I didn't, because we're using CMSIS DSP. A funny story behind CMSIS neural network. We had a student that initially integrated that and got it working. I thought, oh yeah, sweet, we'll push it upstream. And then 6 months later, someone came around and said, oh, this system doesn't have a maintainer, so you contributed it, off you go. So we use the right tool for the job, not necessarily the one that I'm responsible for.
Okay, another question. So you are using basically the core, the Cortex M, whatever you have on this
M4, M33, yep.
As the device for doing all of the machine learning and inference and so on, right?
Yep.
Would it actually help to have an accelerator or something dedicated to do this part, or is the Cortex M enough for you?
For this particular application, it wouldn't help. The execution time is not a big concern, as you sort of, like 20 milliseconds every 5 seconds may as well be nothing in terms of energy. The cost of spinning up a hardware accelerator is probably significant. Mm-hmm. Again, if you're looking at more complex algorithms, like anything image processing, I imagine would 100% benefit from hardware acceleration. But in this case, where even though 50 hertz isn't necessarily low, it's also not a lot of data, right? It's relatively easy to iterate over this. And like over time, the algorithms have improved as well. Like you might have noticed in one of my previous examples, it said 44 kilobytes of ROM, right? But this new algorithm with 2 kilobytes actually performs better. So over time, it's more efficient anyway.
So I think it's interesting that, I mean, you're able to get all of this information solely from an accelerometer, that what a cattle is doing. Is that right?
Yeah, that's correct.
Have you considered like any other sensor inputs to maybe refine that, or does it even matter, like microphone, heart rate, temperature, that kind of thing?
So I would say like more data is not necessarily always useful. So as I sort of mentioned with the gyroscopes, like we have the data there from the training sets, but when our machine learning guys looked at it, it doesn't really help the outputs. And then when you consider the fact that, okay, the goal is to get this running on an ear tag. The ear tag has a small battery, it's solar powered, and it needs to last forever. So these things run at sort of in the 0 to 100 microamps average current range, right? A 50 hertz accelerometer, the Bosch one we use, 10 microamps. 50 hertz gyro, 1.2 milliamps. Like it doesn't make sense for the application. And the fact that it doesn't really improve the performance just makes it even sort of worse. Same thing with microphones, you're probably not going to get away with, if you use PDM mics, I think there's a couple hundred microamps is sort of average. An actual like analog microphone is going to be milliamps. Like heart rate, it's a form factor thing, like on the back of a neck. Like it's got to be IP rated essentially. There's no real way to get like a heart rate sensor out of it. If you're on the ear, there's no real blood flow anyway to measure that. So the only sort of accelerometers are cheap. They are relatively reliable. They are super low power, and they provide a lot of information for the energy cost.
Makes sense.
So are you doing all of this on top of upstream Zephyr, or are you using the Nordic SDK for all of this?
So the main base is upstream Zephyr. For each release, we have our own branch with bug fixes and various functionality, which for whatever reason haven't upstreamed. But the base is standard Zephyr. Yep.
Okay.
Have you looked into using data that would be more like environmental data, like to the point of not using data that's not useful, like gyro, etc., but things like ambient temperature or like the actual environment of the cows?
So temperature is an interesting one because there's multiple kinds of temperature measurement. Environmental temperature for these sensors is not easy to get, and I don't believe it's that useful. And the reason why it's not, well, it's easy to get, it's not correct. So these things are sitting on the ears of cows. The ears of cows are sitting in the sun. It's totally reasonable to see a temperature of 60 degrees on the ear tag or in the collar, right? Like, sure, that's what the temperature of the PCB ends up being inside of it, but it's not necessarily related to the actual ambient temperature.
Yeah, and my point was trying to use maybe like weather forecast information kind of stuff and feed that into the algorithm as well. Like
So,
maybe on the cloud, I guess, or like when you have.
So the challenge with that is for the ear tags in particular. So the collars have LTE connections. The collars themselves are Bluetooth and satellite. The satellite is uplink only. It's 9 bytes, and it's once every 6 hours. So there's no way to get that sort of information back down. I agree in the collar case it could be used, but the collar is not the end goal. The ear tag is.
I was just wondering, is there room you see to improve as far as like the different type of behaviors that can be distinguished, or do you think this is a very good, like, accurate, I guess, data gathering? What I'm asking is, are there other types of behaviors that in the future you would see as being useful to distinguish among?
Yeah, for sure. Even between the research collar and the ear tag, it actually outputs slightly different like categories, just because of the amount of data that we had to train the models on. It really comes down to how much data do you have to try and train these models on in the first place. Drinking is much less frequent than grazing, but it still happens every day. If you're looking to detect something like estrus detection for the cattle for breeding purposes or whatever, that only happens sort of once a year sort of thing. So there's definitely more, and like this is just for the current state of the animal, right? Like there's plenty of other machine learning opportunities in terms of like disease detection, all that sort of stuff. It's just, can you gather the data to train the models in the first place? And yeah, do you have enough to differentiate between things which can look very similar? Yep.
Aren't there like spots where the drinking happening that you can identify by the location of where the cow is to say that it is drinking? There is no way it would be grazing at this spot.
Yep. So one of the cool things about this platform is that it does actually enable device-to-device communications. On the ear tag side, it's a bit too power hungry to listen on Bluetooth to hear, like, you could easily have a tag on the water trough which says, hey, I'm a water trough, and use that as a like, if it says you're drinking and you're not near a water trough, well then your algorithm is wrong, right? To use it as a feedback mechanism. Yeah, on the ear tags, the power, like Bluetooth is relatively power hungry to listen for, so it doesn't quite work. But on the opposite side, you could easily have a device on the water trough which just listens all the time and goes, all right, sweet. This is the times all these devices were near me drinking, and use that as a annotation for the training framework. Yeah.
Couple of questions. The first one that's on all our minds probably is, does this make the steaks taste better? And what?
Probably doesn't make the steaks taste better, but the guilty conscience, yeah.
So did you have to do anything special to get down to this low power numbers in Zephyr, or was it just already there for free?
So I'll use this opportunity to sprinkle my talk tomorrow, which is device power management, the journey to 5 microamps. But yeah, so over the last like 3 years, for example, since we started using Zephyr, the power management aspects of it have vastly improved. At the beginning, it was a lot of out-of-tree hacks and fixes to make this stuff run low power. these days, it's mostly an issue of driver support. Do the sensors you're using support the power management APIs? And basically, it's a question of, are you currently using it? If no, turn it off. So writing your application in a way that only runs the things when they're needed and not just because you can, because in this case, you can't because you'll go flat.
Right. Thank you for the presentation. I have one question around the training data set.
Yep.
You mentioned that you guys have been working on this project for around a decade. I'm wondering how much data or how much can you share in terms of, like, I don't know, months of like data being recorded, which is classified or something you had to gather to confidently iterate over and over your model?
So I think from like, there's, hasn't worked properly, has it? There we go. Like this is like published research. You can, if you're interested in the particular details, you can go look at these links. From my understanding, the current model is sort of trained over somewhere between 8 and 15 data sets. So it is, even though trials have been running for over a very long period of time, over time you like change accelerometers and stuff, the parameters and how these things behave either improve or change. So you do need to sort of look at more at data that's relevant to your current platform. And the project has been running for like over a decade, and it's a process of continual improvement, state of the art. Like a decade ago, 100 microamps average power probably wasn't possible, right? We've got papers on the walls where ultra low power IoT node averages 15 milliamps. It's like, that's pretty funny now, right?
So I noticed the same sensors in the giraffes. Were there other animals other than cows and giraffes that you were able to use this device on?
Yep, so the ear tag, oh, did I show this? Yep. So the ear tag itself is a commercial product. You go to the website and buy it. It's not made by us, it's a commercial third party, like CSIRO is a research organization. But there's been people buying these to use them for a whole range of things, from giraffes, rhinos, koala bears in Australia. I think it was used on a couple. Phil, what else are the use cases? Cheetahs, lions, rhino, yeah. Like, like wildlife researchers are used to spending a lot of money on hardware to sort of track these things. They're not necessarily cheap, but they are very cheap compared to some existing solutions. So, and the fact it doesn't need infrastructure as well, super handy in some situations. So yeah, many species.
And a small follow-up question as well, related to the grazing. Did you compare, and it's a little controversial, veal cows versus grazing cows, and the feed rate compared there?
Sorry,
Veal cows, like cows raised more in place.
So most of the comparisons to date have been between breeds of cattle as opposed to, Angus versus Brahman versus whatever, and also location. So as you might imagine, a cow grazing in Switzerland is exposed to quite a different environment than one grazing in the middle of outback Australia. That's been more what it's been focused on as opposed to, the purpose, I guess, for which it's being raised. I guess from a high level of feed efficiency, this mostly matters when the cow is growing. So you want to optimize that process. Once it's reached its maximum size, that's probably the optimal time from a climate perspective.
So when we're just out of curiosity, so the farmers using those specifically for the cows, not for the wild animals, what do they do with this data exactly then after the data they get from those colors and those ear tags?
So in Australia, data from the collars they don't really get because that's like internal research stuff. For the ear tags themselves, the initial sort of value proposition is that Australia has like ginormous farms. There's no infrastructure, and the sort of state of the art to finding your cows is when it's time to gather them together, you jump in a helicopter and fly around for 3 days, and you try and find your herd, right? If even like a handful of cows have these tags on them, they generally stay in a pack. You know to a relatively close approximation where most of the cows are. makes it much more efficient to go and find them. I think the largest farm in Australia is about the size of like Denmark, right? So like, they're big.
That's location, right? I was talking more like what they're doing during the day, like the behavior ones. What can you do with that data that's useful?
So basically, the conversion sort of goes from, okay, well, how long was the cow grazing for? Based on assumptions about where the cow is, how much grass has it eaten in that time. From that, you can sort of go, okay, well, it's ingested about this much. There's like a conversion factor to sort of go from that to like methane for like greenhouse gas emissions.
Right.
It's becoming more important in terms of like food provenance as well. Like where are these things being kept? Well, not being kept, but where are they spending their time? And how intensive is the emissions they're producing? Yeah.
All right, thanks.
All right, that's it.
Is that time, or is there's more questions?